just into something, or you want the model to do some intelligent decision for you, that is what then it becomes, because then your output will not be correctly right. Now, so one of the reasons why we are more interested in the data processing, or if we call it pre-processing of the data, the word is pre-processing. So we are trying to fine-tune the data to get a very good and reasonable data, so that when we say that this is, the model is saying that indeed the number of students we have here, there are only 5 females and then so and so males, then we are, the probability of we being correct is about 98 point or 99 point something percent. So the data, as we said the last time, is one of the most critical aspects of the data pre-processing, is one of the critical aspects of machine learning model. So we spend most of our energy and time in this area, just to make sure that the data that we have is correct. Because if it's not correct, then your model, whatever you are predicting, is just waste of your time. You are just doing something. Trying to make sure that we said, okay, when you have the data, how do you eliminate duplication? So we took you through the how to find duplicate data, and then how to eliminate duplicate data from your system. Sometimes it is a bit tricky, because you may have data that is legitimately okay, because you may have a situation where you are looking for, let's say, name, and you are looking for duplicate names. You may have the name, you may have a situation where you have 2 people called Inocte. So if your focus is on just Inocte, then what it means is that you may have 3, 4 people called Inocte. Do you kick all of them out to just one? No. So you have to move further and see what is the next step. So you have Inocte, Enoch-K, then you have maybe another one, another name there, Yao. So then you figure out. So these are, you go through your data, and sometimes, so in trying to kick out some element that you think they are duplicates, this is where sometimes the expert knowledge also comes in. So when you are doing something, you are not doing it in isolation. You need to consult with the people who have knowledge in that area. For example, I work on a number of things, but in health area, I'm not a health person. I only apply my computer knowledge to solve health problems. So I liaise out to people who are in the health sector. So I liaise with the biomed people and say, okay, when you have this, what does it mean? Is it correct? They will say, oh, well, we too, we don't really, yes, but I'm not too sure. Then we say, okay, who are the medics? If it has to do with the medics, then we contact the medics. So this and this, is it correct? They say, oh, yes, you may have a situation where you have duplicate numbers like this. In that case, then we keep it. But we should also be mindful that that duplicate, if it's not a unique identifier, it may likely cause a problem somewhere. Now, where you have 2 different patients having the same information, that is okay. But where you have the same patient, or maybe we have maybe the same patient with different information, then this is where then we have to figure out where the problem is. So cleaning the data through with duplication, it's very important in helping us get a true reflection. Now, what exactly when we say we are doing the model we are interested in? Now, whatever you have, we didn't want to bother you too much with the detailed mathematics or mathematics behind those things. But it is purely based on, see that when we started, we talk about, oh, your knowledge in statistics. We talk about your knowledge in statistics. We talk about this. We talk about this. Some basic mathematical equations. These are fundamental things, but we don't want to bother you with those things. That is why we are going straight into the use of those things. But as you go higher up, then you see that the mathematics are very important. Now, why am I bringing this in up? The data that you have, what your model is trying to do is to learn the relationship that is inside that data, trying to find out relationships that are within that data. So all that is learning is the relationship in the data. So if there is duplication, the relationship is the same, that is what it will learn. So when it's going to predict for you, to predict that same thing for you, because that is what it has learned. It has learned from your data. That is why we are interested in this data pruning or pruning the data. Now, the second thing also that we taught you was what we call missing data. Missing data. Now, if you are collecting the data, that is fine, no problem. Then you'll be very meticulous in your data collection. Maybe, I think the last time I was trying to mention something. You are supposed to look at track the way you eat every day for the next 365 days, 1 year. I'm sure there may be cases that you will miss what you ate. So when you have such data gathered over the years, those missing data, what do you do with it? If you don't deal with it, then what it means is that it may assume that it's a trend that day you didn't eat. So it means that various segments that you may have, it may be seen as if there are a number of days that you don't eat. So then when your model has to predict, it will predict that, oh, today you won't eat. Because that is the knowledge it has acquired over the period through the relationship that you have in your data. So one of the things that we also do is, though we identify those data that are missing in the records that we have. And then we figure out these data that we are missing, what are the best practices that we can use to fill in those data? Use interpolation. So there are various methods that we use. And I think Ken the other time also mentioned some statistical methods that we can use to fill in those missing data. Then there is also something called outliers. Something called outliers. So those outliers also very strange number. Sometimes you are typing and you type something wrongly. I've just finished grading. I'm almost wrapping up with my grading of scripts. And you see that sometimes students are just typing some mathematics, 22 times 3. Then they write a wrong number there. Now, do you mark the person wrong, give the person 0 because the person has done that? So this is a reason why we go through what we call your steps, or I go through your steps, and then find out, okay, if the total score is 5, and the fact that I follow through and you see that just that multiplication alone gave you wrong, then I'll give you 4.5 over 5. Sometimes, depending on the equations, if there are a little bit more work that has to be done, the answer is wrong, I end up sometimes giving you 5 over 5, which I can defend because the focus is on the answer. But if my measuring there is not the answer, but your process of arriving, then I give you everything, even though the answer is wrong. So when it comes to things like that, outliers, again, you see that what I've just explained, I'm a human being, so I'm using certain processes to determine what you should get. But when it comes to the machine is learning, that is the relationship it learns. So what we then do is when we have situations like outliers, then we figure out how we can identify those outliers. And again, Ken explained these things to you the other time, how we can identify outliers. And there are clear methods that have been, if you call it, tested on how we can manage these outliers. And again, he took you through some of those things. Apart from the outliers, there are also, we've talked about duplicate, we talk about missing, we talk about outliers. There are also some issues associated with the data, which we call, sorry, something that which we call distribution. Again, it has to do with statistics. And the last time, I think he was also sharing with you what you call histogram distribution. Now, again, this is very important. And I remember he mentioned that the last week also. When we are dealing with numbers, we don't want the model to skew its decision based on what we call majority-minority groups. We don't want the model to do that, because if we have more males out of the group, if we have about 90% of the students population are males and only 10% are females, when you give the information, because that is the trend it has learned, so there is more likelihood that it will predict male decisions compared with female decisions. And that is what we call class balance. So when we are dealing with models also, we try also to make sure that we have a mechanism for balancing the distribution so that the model will not be biased towards a particular distribution or a particular decision. So one of the things that we do also when it comes to the evaluation metrics, we talk about it. One of the things that we do also is first to make sure that the distribution that we have is fairly distributed. Otherwise, we will have what we call, the model will be what will lead to what we call overfitting, or it will be led with what we call underfitting of the model. So these are some of the reasons why we focus a lot on the data. As for the model development, once you have our data, it's a straightforward process. So I will leave the platform now for Ken to continue with where he left, because we said we are going to start with you also today on how to start with a model. So Ken, I hand over to you for the next phase.
All right. Thank you very much, Dr. Mills, and good morning to everyone. So today we are going to start off with the model development. And before we start, let me quickly share with you something. So what I intend to do is I'm going to do about a 20-minute presentation that will summarize everything we've learned so far. And right after that, we are going to build a model, a machine learning model to test our knowledge in the various things that we've learned. So if you can see my screen, I hope you can see my screen.
Yes, I can see it, but I don't know about the others.
Okay.
Yes, please.
Okay, thank you very much. So now let's quickly move on to what I have over here. Like I rightly said, everything I'm going to talk about is something we've spoken about earlier on, especially when we started with the introduction. So this is going to be the presentation outline. I'm going to walk you through a brief introduction. Then we are going to look at what machine learning is, supervised learning, unsupervised learning, and we are going to look at some machine learning algorithm. At least this is going to prepare the grounds for we building those models. So over here, I'm not going to waste much of your time. Like I rightly said, most of the things I'm going to cover have already been done. So you can quickly do a reference from the first material that we shared, and that's precisely section 1.1, page 5. And let me quickly do so because I believe these materials are with you already. So let me just go back to this. And yeah, I think this one. So if you don't have it, because maybe you joined later, I'll share that again. So this was the introduction Dr. Mills gave us, and this is the page 5 I'm referring to. So over here, we get to see some definitions, and that's going to set we on the right path. So let me go back to my presentation and let me continue from here. So we said machine learning is a computational learning where algorithms are used to extract information from raw data, and preferably we want a very large data or data set, and we represent it in a type of a model. Now, ML essentially learns from that given raw data through some experience and make predictions or decisions based on the data it has learned from without explicit programming or being programmed to do so. So before we even talk about machine learning, we need to understand what traditional programming is all about, because eventually in that presentation Dr. Mills gave, there was some comparison that we did. So with traditional programming, especially with this block diagram, we are going to present our computer with some data, and then we're also going to present some rules, and the computer is going to work on its magic based on the rules you have presented it, and it is definitely going to give you an output. So I have a short simulation over here. We are going to see something like, let's say we input 2 into our computer system, and then we input another data 3 into our computer system. And now the rule we have over here is, for instance, addition. So the computer will do its computation, and then we get an output of 5. Now, this is something we are quite familiar with, especially with this code snippet, as we see over here, because we wrote some of these code ourselves. So for instance, on line 1, it is more or less what we have over here. We're trying to input 2 into the computer memory. So we are saying that first number is equal to, we are doing a typecasting over here, and we are using the input function to accept some data into the variable first number. We do same for line 2, where in this particular instance, we're expecting a 3 over here. And then line 3 is where we apply the rule, because over here, we are using an addition rule over here to add these two numbers, first number and second number. And then we are expecting an output from line 4. So this is the traditional programming, where we are giving instructions to computers based on some logic, predefined rules or logic. In the case of machine learning, it is a little bit different, because over here, we provide the data, and then we provide the outputs. We provide these two to an algorithm, which in this case, a machine learning algorithm. There are several of them, okay? And we are going to learn a lot as we move along. So we are going to provide the data and its corresponding output to some algorithm, and then we expect to get a rule, and out of the rule, we can make predictions. So over here, the primary thing is the data that we'll be working with, and that's why we spent a lot of time looking at the data pre-processing and all the things that we learned prior to this. So our data may look like this, and in our data, for instance, we have x1 and x2 with a corresponding y, okay? And then what we do is, okay, we can split this data into 2. So the split you see over here with this section is going to be the input data, where x1 and x2 are the input data. And then indeed, y is going to be the output end of the data. So at the end of the day, back to our block diagram, our data is going to be this x1 and x2. We feed it into the algorithm, and then our output also comes in here with our y. We feed it into the algorithm, and then we learn the algorithm learn some inherent patterns within this data that we have presented it to give us a rule. So over here, it turns out that, well, after algorithm learns, it comes up with a rule called addition. Now, there's no machine learning algorithm called addition, but just so this for you to get that basic concept of how this learning is done. Because what I ended up doing over here with this random selection of data set is that, okay, well, the relationship that lies between x1 and x2 with respect to y is that when you add these two numbers, you get your y. So for instance, 2 plus 3, we are getting a 5. 4 plus 5, you are getting a 9, and so on and so forth. So we get the rule over here. Now this rule then becomes a model. So now let's go back to the definition, once again from section 1.1, page 5 of that material. Now we are saying that ML essentially learns from data. So as you saw, we just presented data and it was able to learn. And then we can make predictions based on the data learned without explicit programming. So we are not going to tell the data or the system that, okay, if you see 1 and if you see, for instance, if you see input 1 and if you see input 2, add them. No, we are just presenting the data for it to inherently learn from that data so that we can make some prediction. And at the end of the day, after learning from that large data set, we want to present this in a type of a model, which is more or less that learning rule. So over here, we get to a point where we can make predictions. Remember, we have been able to learn and get a model, which is the addition model. Okay. So now we can input some data. And remember, this data or this new data I'm bringing up over 100 wasn't part of our original data set. Our original data set didn't have 100. Now I'm bringing 100 over here, and I'm also bringing 400 over here. And it turns out that because some learning has been done from a previous data set, which had some numbers, and we're able to get that learning rule as an addition, we put this together, and then we get a forecast or a prediction. And that's going to be the basics for we building machine learning models. Now, it turns out that what I just demonstrated is not really a model or an algorithm, okay, but just to set you on a good path. Now, what I'm going to show next is actually a machine learning model that we can build. So over here, I have some data sets, okay? And the thinking I had, these are just randomly things I just put in over here. Okay, I didn't even write any code to this. I mean, I just had one column as age in weeks and then another column as weight in newtons. And what I was thinking is, okay, maybe there's a hospital and maybe at the children's ward, parents come for weighing every week, okay? And part of the things they do, I believe, is to check the weight of newborn baby. So my thinking was, okay, so there's some data that's collected at the weighing ward. And then we have the average age of, let's say, all babies that are about 2 weeks old weighing as 12.0 newtons, all straight to babies that are about 20 weeks old weighing about this, okay? So these are just random numbers that I picked. Now, what we can do is, let's assume this has been happening, and then maybe that weighing scale breaks down, and for which reason we cannot apply the same process, but then maybe getting the weight of babies is very important. So maybe somebody comes in and the person is about 12 weeks old. If the person is 12 weeks, well, if the person was maybe 5 weeks, we can just do an extrapolation and say that, okay, for most of the majority of 5 weeks, they're about 18.5. But in the case of the data that we have over here, we don't have anything precisely 12 weeks. So it will be very difficult for us to make that assumption or prediction. And this is where machine learning comes in. So what it happens is we can actually feed this data into a machine learning model where we are going to train this data based on what we have over here. And in doing so, we come up with this very interesting one. Now, this is something we've seen before, right from secondary school, okay? Now, what I've done over here is just plotting age versus weight, okay? So on my y-axis, where's my cursor? Yes, on my y-axis, I have my age in years. Sorry, this is supposed to be in weeks, okay? Sorry about that. And then on my x-axis, I have my weight in newtons. And all that I've done is, okay, so 0.2 and then 12. So age is about 2 years and this about 12. So this is the intersection. So I put a dot over here. Then 4 and 16. So age is about 4 and this. So you get the point, okay? And I actually did this in Excel. So after doing this, then based on secondary school, okay, we can draw a line of best fit, okay? And that line of best fit, the concept is, okay, now let's draw a line such that it at least passes a minimum of at least 3 of these points that we have plotted out over here. So I have my line of best fit in this red dotted lines, as you can see over here. Now, in this line of best fits, it is interesting to note that, yes, we can have some kind of a learning rule. And the learning rule we deduce or get from this is nothing but the line of the equation of a line, okay, y is equal to mx plus c. And of course, we know what m is, which is going to be our slope, and then our c is going to be our y-intercept. So over here, we can, I mean, physically, if we were doing this in a class, I would have asked you to, I mean, calculate the slope yourself, okay? And then we can extend this line to actually get that y-intercept on that negative end. Now, it turns out that this is the learning rule that we get. Now, interestingly, if somebody is 12 years old, like I was trying to say, okay, so this is 10 years, somebody is 12 years age. Now we can trace this up onto this line and now do a prediction back over here. And that's exactly what we get, okay? So we are going to see that, okay, if somebody is 12 years old, even though we don't have anything of this kind of precisely age 12 over here, we can actually make a prediction based on the model that we have. So over here, we can simply do how do you call it, a change of subject, okay, because over here we are trying to find, okay, we are finding x, okay, x this, so we can do a change of subject, plug in y is 12, and then our slope is what we have over here, and then we put in our y-intercept, and we can get some value of, let's say, a 33 point something in terms of the weight, and that's what we want as our prediction. Now it turns out that this is what you see a lot of economics and other people refer to as a linear regression, because indeed we have a line which is linear, okay, something in a straight line, and then we have been able to build a regression model out of this. Now, back to this. So you can actually
Ken,
find
sorry,
this
can you go back to that line, please? Ken, can you please?
Okay.
Of the baby, you can also tell the age.
Yeah, sure.
Malnourishment, whether the baby is malnourished or, and so we can do all sorts of things with data. We can classify maybe those children that come in and they are malnourished and those that are not malnourished. We can still use the same thing. So you see that with data, there are too many things that you can do with machine learning. The basic thing is your understanding of what the thing is. And this, what he mentioned, linear, it is one of the machine learning models that we will learn. We will take you through, called linear regression analysis. Ken, please go ahead.
All right, thank you very much, sir. So we get this to this point. Now let's look at what we had over here. So back again, this in the page 7 of that section 1.1 presentation Dr. Mills did. And over here, we're trying to look at the comparison between the machine learning approach into solving problems and also the traditional programming approach. So we say that with the conventional learning, or we're trying to use the traditional programming approach and the machine learning, we see that the traditional learning uses structured data and rules, like you saw in the earlier simulation where we're having 2 and then we're having 3 and the rule addition was added and then we saw what we saw. All right. Now, we first create an algorithm by specifying all the rules. Then we present the data to the rules like you saw. And then the rules operate on the data. So the rule was addition, it operated on the data that we presented 2 and 3 and we got an output of 5. But then in the case of machine learning, we use complex structured or unstructured data, and then the algorithm handles the feature extractions automatically. Now, we present the data to the algorithm, not rules. So over here, we saw that the algorithm was a linear regression algorithm. And what happened next is we present the outputs, okay? Or it learns from the answers. Now, the algorithm learns the rules that maps input to output. So over here, you are seeing that, yes, it is basically mapping some input to output. And eventually, we present some new data to make some predictions. So over here, we are presenting 12. 12 was completely new to make a prediction that we are getting over here. And there's nothing different from what we learned back in secondary school. But then there's an issue over here, which we are going to discuss. So over here, also on page 13 of that slide, we get to understanding where, okay, not all algorithms are going to work for all use cases of our problems, okay? Because look at this over here. Now, if you are to critically look at this, okay, and okay, so over here, we just have 2 variables, and then we are having 2 axes. Imagine there are 10 variables. That means we should have 10 axes, okay? Now, if it is 3, maybe 3 is, okay, we can have a z-axis, okay, which is going to show the depth, and we are going to have the plot. But then if we have 10 variables, that means we are going to have 10 axes, which is practically going to be very difficult to even visualize, not to talk about having a straight line to cut across 3 points that is picking from all the 10 axes. So definitely linear regression has its own limitation. And that's what we are trying to pinpoint over here, that in selecting an ML model or an algorithm to solve a task depend on, first of all, the data type, okay, or the structure of the data. So over here, looking at the structure of the data, we can see that, okay, linear regression can help us. But then if the structure is like that, okay, we have, let's say, a data set that has about 10 inputs, then linear regression is not going to help us. We can use other algorithms. So over here, the problem is important, then the data or the structure of the data. Now, the style of the ML that you want to build, the task, is it a regression task or a classification task? And we are going to see the differences as we move along. Now, when we say classification, I mean, I'll say the name is quite intuitive, okay, in a sense that we are trying to build something and put it in a class. So we are trying to do some class, okay. Now, a regression means, okay, we are trying to build something that will predict a particular value for us. So, or the depth of the learning, whether we are doing a deep learning or a shallow learning or any ensemble learning or any other thing that we want to do. So over here, we get to see this tree diagram, okay, and the first thing we need to analyze, okay, what kind of problem? Do we have labeled data? If it is yes, then of course we can do supervised learning. If the data is unlabeled, then we'll look at unsupervised learning, and then we go on and on with these things. So please, I'll highly encourage you to go back and do a quick preview of those materials we shared earlier on. So now I have done a little bit of modification over here, and this is what I was pointing at. Okay, so with this one, this original data set, yes, we have just 2 inputs. We can just plot it on a y and x axis. Now over here, we have about 3 or 4, okay? And in this case, I've added height and then gender. And now the problem has changed a little bit in a sense that, okay, now I have some data with labels. And the labels I have over here is either male or a female. And what I can see over here is, okay, I've also added another one over here. So over here, I don't want to do a regression. I want to do a classification. So maybe giving the person's age, the person's weight, and the person's height, what gender are we going to classify that particular baby into? It turns out that in some places, some of these data will make sense, okay, but then in other use cases, it may not. But just to make you understand why some algorithms will not be sufficient to solve other problems. So it turns out that, well, then in this particular instance, we can actually look at a classification model. And in this classification model, we are going to rely on neural networks. Now, it turns out that neural networks falls under all these things that we can do. So for instance, if you are looking at classification, you see we have neural networks over here. If you are looking at regression too, we have neural networks over here. So we can practically use neural networks for quite a number of things. And that's why we are going to emphasize a lot more on neural networks and also with the other algorithms as we learn along. So over here, the neural network is a massively parallel and distributed network made up of simple processing units called the neurons. So this, we draw our inspiration from the biological human brain because that's where the actual neurons are. But then we are modeling, or we are trying to engineer or have an engineering model of that artificial neural network. So of that neuron actually. So the artificial neural network are inspired by the structural and functional characteristics of the biological human brain. And that's to say ANNs operate in a manner such that they mimic the operations of the human brain. So over here we have this is a biological neuron, but then the engineering model will look a little bit different. Now over here we have this architecture and structure, okay? Now we've said this over and over again that in this particular architecture, we can have the input layer, which is definitely going to be the input, and then the output layer is going to be the output. And later on, when we start building the model, maybe in the next 10 minutes, you are going to see what is going to inform the number of neurons we put in each layers. And then in between the input and the output layer, we can have that hidden layer. So now let's go deep into a little bit of this engineering model of the neuron, because the natural neuron in our brain doesn't look like this. We have engineered this and we have put some few things over here. Now, there are some key parameters that we need to look out for, which is the input features. Now, these input features are going to be from the data that we have, okay? And then we are going to have some weight, which is going to be some randomly generated numbers. And I'm going to explain to you why these weights are important and also some biases in a lot of instances. So at the end of the day, this is a very simple mathematical operation that is performed, and it's going to be a product summation of all the inputs and their corresponding weights, and we are going to pass it through an activation function to get our output y over here. So now let's look at specifics. First of all, the inputs. Now, in artificial neural networks, the input refers to the data or the feature provided to the network for processing. So over here, Rx or our inputs are going to be some values, okay, that we got from the age and the weight. Now, each input corresponds to a feature or a variable in the data set that the ANN is attempting to learn from. So these are the variables, and these are the input features that we have. In this case, this is also going to be the one. Now, yes, and that's what we see over here. Now, let's look at the weights. And in order to understand these weights, I discovered something very interesting when I was doing some research. So now, this is what I have. Now, let's assume we are doing a research on electoral violence in Ghana. And I picked this controversial topic because, of course, we are in an election season and we are not hoping to see any violence though, but then this is what probably will resonate with a lot of people. And in our research, we have a sample size of 50. But it turns out that within that 50, we have two clusters, okay? So we have the first cluster made up of 40 people, and then the second cluster is made up of 10 people. We want to see how weight is very important in doing some analysis over here. So this is, let's say, the population that we have, or our sample size, okay? And over here, we can count. So we have the red is going to be the second cluster made up of 10 people, and the black is going to be the first cluster made up of 40 people. So now, let's assume we pose a question, or we ask a question: can money influence electoral violence? So it is either going to be a yes or a no. Okay. Now, this is the profile of the first cluster. Let's say randomly selected students from the University of Ghana, randomly selected, okay? So maybe the survey team went into the various halls, the various lecture halls, night markets, I mean, random places at the university, and selected 40 people and saw their views. And then the second cluster, and I'm putting this very important over, the second cluster were carefully selected individuals. And these individuals include, out of the 10, includes the IGP. And I'm bringing these individuals up because of the topic we are dealing with, which has to do with electoral violence, okay? Because I believe the Inspector General of Police has more knowledge on electoral violence than any randomly selected University of Ghana students. I may be wrong, but then in most cases, that's going to be the case. Then we also have the NCC boss, that's the National Commission for Civic Education boss, who is well versed in some of these things, the Shraj boss, the Chief Justice, because at the end of the day, if there's some violence and it ends up in court, it is going to be in front of the Chief Justice. Then I put Professor Jampo over here, who is an academic lecturer at UG. I believe he's a UTAC president, but beyond that, he's a professor in political science. So definitely he has more knowledge. I believe he has done a lot of research into some of these topics. Then we put, or we select ex-President J. Kufuor, who has been at the forefront of probably not perpetrating violence, but maybe some of them could even have been victims of some of these electoral violence, okay? Then I put our very president, Nana Addo Dankwa Akufo-Addo, our ex-president John Mahama. In fact, I needed to balance this up because there were some NPP and NDC figures over here. But then we have also the Speaker of Parliament, who has been in Parliament the longest and has ended up being a Speaker of Parliament. So all these people, and General Mosquito, all these people are very experienced politicians who definitely know more about some of these things, especially with this particular topic, than randomly selected University of Ghana students. Let's say if the topic was about maybe the use of social media, then definitely the randomly selected University of Ghana students are most likely to have more knowledge on these social media apps than the people I've selected over here. Okay, no disrespect, but then these are the realities that you are dealing with. Now, the point is, the question was, okay, can money influence electoral violence? Now, let's assume 40 of all these people from cluster 1, randomly selected, says no. And the 10 over here says yes. If we are to use an unweighted analysis, then we are going to have 40 for them. But then we are given a weight of 1 over here. So with a weighted, we are still getting 40. Now, in the case of these experienced people, the unweighted is 10. But then if we are to provide a weight of 5, then the weighted becomes 50. Now, this is very important in the particular analysis that the social science people are going to do, in the sense that a lot of the time analyses are made and it's like, okay, majority said yes, so it is going to be for the majority's sake that we are agreeing with them. But then the point is, when we apply a weight over here, all that it means is, okay, the knowledge of the IGP, we are putting a weight of 5 on it, and the knowledge of a randomly selected UG student based on this topic, we are putting a 1 on it. That means the IGP's concern, or the IGP's knowledge, is about 5 times that of a randomly selected University of Ghana student's knowledge on electoral violence. And that one, I'll not be unapologetic about that. That can be factual. But if we don't apply weight on it, and we just go by these raw unweighted numbers and do our calculation, then we'll end up getting some results or some answers that will be, that will not communicate the real issues on the ground, especially with this particular topic. So over here, when we do an unweighted average of all these answers that we have over here, probably we are going to get 40 over here, and we are going to get 10. And anybody reading this report will know, oh, if 40 people said this, then it means that is the case. But then if we weight them, and we got to, even though the people we selected over here were just 10, but then based on their weight, their value at the end of the day is becoming more relevant than what we have over here. Now, it turns out that what we have over here, the quantity multiplied by the weight, is nothing different from the formula we saw with the product summation of our xi multiplying our wi. But then let's come back here, because we are still dealing with this problem. And over here, yes, we have the ages, the height, and the weight. And over here, I've changed the gender into some categorical input. So we have 0 for females and then 1 for males. So now this is what is going to happen. And I'm just going to select one particular row, but then it's going to apply to all of them. So on this particular row, yes, the formula, as we can see over here, still applies. So our xi multiplying our wi. So our x1 multiplying our w1. So x1 is going to be like this 2, and the randomly generated weight. And then our x2 is going to be this, and some randomly generated number, which is going to be our weight. And our, how do you call it? Our our x3, which is going to be this height, multiplied by randomly generated weight. So over here, the values are what I have them over here. And the ones I have in red are those randomly generated with, and I just said randomly generated. At the end of the day, just as we saw with the case of the UG students and these IGP and all those people, we want to find, because as it stands, okay, we don't know if in the prediction of gender, weight or age is more important than weight or height. But then in the case of what we just saw, based on the topic, electoral violence, we can just make that intelligent guess and say that no, the IGP is going to have more knowledge than any randomly selected University of Ghana students. So those ones can be made. But over here, we don't know. So we select randomly generated weights. Now, this randomly generated, based on what we have over here, you can spend time, later on I'll share the slides with you, so you can spend time and do this calculation. But then it turns out that the y is now going to be a 0.38 if you do this computation. Now, this 0.38 is not the same as our 1 over here, because we're expecting a 1, but then we are getting a 0.38. So then there's an error. So this is going to be, our target is our 1, and our output is our y over here. So it turns out that we are going to get an error where we are going to say 1 minus a 0.83. And this is going to be the value of the error. Now, this value of the error is going to be sent back to update the weight, because at the end of the day, the input is still going to be the same. It is the weight that we want to adjust to an appreciable level where we can say that, okay, this input is coming in and is going to be multiplied by this weight. And when we build the model, we are definitely going to see the weights. So over here, we have these two equations where we use this to update the weight. So the new weight, or no, let's go to the equation 3 over here. The change in weight, okay, is going to be our target minus our output, which is definitely our error, multiplied by the xi, which is still that same value. And then there's going to be a step over here, which is going to be the learning rate. So this learning rate, we are going to see when we build our model, is going to be some value we put in over there. And like Dr. Mills said, if you remember very well, if you pick up a very big learning rate, we may miss the optimal value, because the optimal value is getting something which is closer to 1. Okay, so now we update the weight over here. And in this first instance, I'm picking a very big learning rate. So I'm picking 5 over here, just for the first one, okay? But then this is actually going to apply to all the other ones we see over here. So over here, when I update this weight, because remember the formula, our target minus our output. Our target is 1, and our output is what we have over here. And the weight, the xi, is still the 2, as we can see over here. And I'm picking a very large learning rate, which is 5. So I do this computation, and I get a new weight, which is going to be a 0.63. Now, I pick another one where I pick a very small learning rate. So over here, this one was very big, a 5, and this one was a 0.5. And it turns out that I have a 0.17 for our new weight. So I'm going to end, the calculation is going to be, iterative, and it's going to contain a lot. But then the point is, you realize that at each point, our weight is going to be updated. And those updated weights is still going to be multiplied by the values we see over here. And then the closer we are to 1, then it means our model is learning. The weight gets updated and our model is learning. Now, it turns out that if we use a very large weight, learning rate, we'll end up missing the optimal value. And if we use a moderately small learning rate, and I'm choosing my words very carefully, because if we use a small learning rate, then it's going to take a very long time before we converge. But then if we put it at the middle ground, then chances are we are going to do it very quickly. Now, everything I've said, okay, in terms of the architecture of the neural network and the neurons and everything we see over here, is going to be applied to each and every neuron. So every neuron is going to do that computation I just showed. And what I just showed was even a partial one. It wasn't even for the full neuron. So you can imagine how the computation is done. So now let's come back to this, I believe the last slide, okay? And this flowchart diagram is going to summarize everything. So with this flowchart diagram, we get to see that, okay, for our machine learning, we are going to load our data. We are going to do some pre-processing, and that pre-processing involves a lot. If you have missing values, this is where that pre-processing comes in. If we have duplicates, we do that pre-processing. If we have some null values, we do that. If we have some outliers, that pre-processing stage is going to cater for that. Now, it may be different from every model that we build based on the data that we get. Some models, we may not do a lot of pre-processing. Now, it turns out that with this particular one, the example I just showed, okay, where we had males and females, then of course we need to change or do some pre-processing on our Y end, where we are going to change the male, female to some categorical data like we did last week. Now, at the end of the day, after doing our pre-processing, then we get some kind of a refined data. Now we split our data into a training data set and a testing subset of the data set. Now we use a training data set to train our model, but before then we build our model, which is just introducing the algorithm. And then we train our model. We learn, or we let our model learn from the model. And then over here, we evaluate our model with a test data set. And we are going to see all this in code. And finally, we save our model, and then we can deploy our model, whether to an app, a web app, a desktop application, or any other thing that we want to do, which we are eventually going to build as we move along. And then we deploy. So now there's a short simulation over here. So these are data sets, and I have this red outline over here just to show that, well, there's some kind of some bad data set that has some null values and stuff like that. So we do the pre-processing, and then from the pre-processing, we get some data, and this clean data, which we have that green outline around it, we are going to split this data into our testing and our training portion of the data set. Now we are going to use the training data to train our model, and we are going to use the testing data to evaluate or to test our model. And then one of the things we are going to see as we code along is actually going to be what we see over here. So typically this is going to be our data sets, okay? And we are going to split our data. So over here we have 4 splits, or we have, let's say, 4 quadrants, okay? The first one we have over here, let's forget about this line over here, but then the first split you see over here is to specify that, okay, this is going to be the inputs and this is going to be the output, our target, either a male or a female, based on the categorical data that we have over here. And then we're also going to do another split. And this split is going to make sure that, okay, we have the training part of our data, which is going to be our X train, and this is going to be our X test. Now, what we are going to do is we are going to use this X train, and this is also going to be Y train. We are going to use our X train and our Y train to train our data. And then after we get our model built, then we are going to use our X test to make some predictions. And whichever values that we'll get, we are going to compare it with the original Y test and see how good our model was able to learn from that data set. So this is going to be the end of the presentation. Now we are going to switch back into our environment where we can write some code. We have some few minutes, which I believe we can conclude on this. So over here, let's go to GitHub, and I have a repo, and let me quickly do this and share that with you. So we have okay, let me come in here. All right, so I think is this one that we are going to work with for today. So let me share the link with you in the chats. Okay, so as we always do, we click on this code, we download the zip file, and then we do the extraction, and we can start writing our code. Okay, so now let me open this up to do the extraction. Okay, so let me come back here. Okay. Okay, so here we have some few files over here, but I believe what we are looking for is this one, I believe, yeah. All right, so here we have, and over here we are actually going to use some kind of a data that we are very familiar with, which is the iris data set. Okay, now the reason why I'm saying this is you realize that the processes we go through with regards to our data pre-processing and making sure that we are very familiar with our data alone is quite laborious, and we don't want to pick a new data set where we have to repeat that whole process again. All right, today we are interested in building a model, and in subsequent videos, or sorry, in subsequent meetings, we are going to do an in-depth analysis of the model, its how do you call it, performance and other things. Even though today we are going to just have a snapshot of almost everything that involves the process. So we are building a shallow neural network, and when we say something is shallow, of course it means it is not deep. We just have a very small hidden layer in there. So this is what we are going to do. Now, the objective is to develop a machine learning model using a shallow neural network architecture. Now, we are going to use the iris dataset to train the model. We are going to do some performance analysis of the model, and then we are going to use the developed model to make predictions. Now, in the file that we are going to download, okay, we are definitely going to see that included in the materials I have over here is also going to be the iris data set, which is the CSV file. So you are definitely going to have this along the way. So this a different version of that flowchart, but then it's communicate the same thing, because at the end of the day, we are going to load the data set, we are going to do a pre-processing, then we split our data into the test data and the train data. We are going to use the train data to train the model. Then we are going to use the test data to test the model. We are going to make some predictions, and we are going to do some analysis of everything that we have over here. Okay. No, I think, let me check this one. Okay, I think this is the one I needed to open, because this morning I was just testing some few things over here. So let me just close the old one. All right. So it's the same material, okay? Just that this morning I was checking some few things to make sure that everything is intact. Okay. All right. So we are going to import the libraries that we are going to work with, okay? And clearly you could see that we are going to use some NumPy. At some point, we are going to use pandas. And like we covered earlier on, we've dealt extensively with NumPy and pandas, at least for the very things that we'll be dealing with, especially with this particular model. We are going to do some plotting to get some visualization. We are going to use scikit-learn. If not for anything, we are going to do some categorical pre-processing of our Y labels, okay? And then this is more or less a new library we are introducing over here, which is Keras. Now, Keras is part of TensorFlow. So if I'm to do a simple Google search on Keras, okay, and you have to read all the things we have over here. We have a lot of things over here. But then let me just go into this, and then we can just look at the documentation, okay? And there's a lot over here. There's a lot. But then if you just want to install it, you do a pip install Keras. Okay, this is when you already have it and you want to upgrade it to the latest version. And then you can work with this as we are going to do. So over here, what I'm going to do is, I already have it installed, okay? But then you can quickly do like we always do, pip install, and you type in Keras. Now, this is a very big library, and you need a very strong internet connection. But I believe whatever internet you are using is going to make this work. So you press enter, and now Keras will be installed. Now, once you have Keras installed, you can start building this artificial neural network model. So now what I'm going to do is I'm going to import NumPy as NP. I'm going to import pandas as PD. I'm going to import, or I'm going to say from matplotlib, import pyplot as PLT. This we've seen over and over again. And I'm going to say import Keras, and I'm going to say import sklearn. And it turns out that we are going to use Seaborn. So let's do that quickly. So I'm going to say import Seaborn as SNS. These are things we've seen. I think the only thing we are getting to know now is this Keras library. So now I'll do a shift enter to run this over here. So it is running. You could see the star over here. Normally, if it is running for the first time, it takes a while, but then in a matter of few seconds, I believe everything will be complete. Now I have a problem over here. Okay, I think the spelling of the Seaborn is wrong. So I'm getting a prompt over here. So Seaborn this way. Okay, so now everything is looking good. I have all my libraries imported over here. So now let me load my data set. So I'm going to say data set is going to be equal to pd.read_CSV. We've seen this over and over again. And then the data sets that we are interested in, the iris.csv file. So it is iris.csv. And I'll run this. So everything is looking good. Now let me do a quick preview of these data sets. And that's exactly what we know, okay? Over here, there are no null values and other things, okay? But we can still check. We can do the data set.info this way. And we get to see that everything is 150 and everything is showing up as 150 not now. So everything is looking good. All right. So we have loaded our data set, but then we need to define our input and output variables. Based on what we know, we are saying that these labels or these species are going to be our labels, and the sepal length, sepal width, petal length, and petal width is going to be our inputs. Our ID is not adding any value to it. It's just some numerical 1, 2, 3, 4, 5 showing up over here. So now, in order to do this, okay, I want my input. My input is going to be my X input, which is going to constitute sepal length, sepal width, petal length, and petal width. So what I'm going to do is, okay, I'm going to say, so X, I'm going to call this X input is going to be equal to the data set dot I want to drop. Now, what do I want to drop? I want to drop some columns. Now, I want to drop the column ID and also drop the column species. Remember, we spoke about this earlier on. So over here, when I run this, I want ID to be dropped. ID this way, and I also want species to be dropped so that I'll be left with these ones as my inputs or my X inputs. So now I run this and everything is looking good. So now let me just do a preview and see if it has actually been dropped. So I'll do my X inputs this way, and then I have exactly what I have requested for. So I just have my sepal length, my sepal width, my petal length, and my petal width CM. So everything is exactly what this is going to constitute my inputs. Now let me look at my output. And my output is going to be, for instance, Y outputs. And I'm also going to get it from my data sets, which is the original data set, okay? But then this time around, I wouldn't want to be dropping everything. I just want to select a particular one. So I can do dataset.species this way, or I can do dataset, and I'm going to enclose this in some square brackets and then specify it this way. I hope you remember what we did the last time. So when I run this, everything looks good. Now let me do a preview of my Y output. And now that's exactly what I want. So I have my array settles and stuff like that. But then once again, when we come back to, especially based on the refresher that we've done over here, with what we see over here, for instance, if we have male, female, remember it is going to do a calculation and we are going to subtract to get the error. So we cannot have male minus 0.83. Okay, we cannot have female minus 0 point something something. That's not going to work. Mathematically, it is not going to work for us. So in that same sense, the iris setosa, iris virginica, and iris versicolor is not going to work for us. And that's where we need to change the target output to some categorical data. And that's what we saw in action last week. So over here, I can say from sklearn dot preprocessing, I want to import the label encoder, and then I'll run this. So now I can now do the pre-processing. So I can say let's call this Y encoded. So Y encoded is going to be equal to this label encoder class this way. I'll instantiate it this way, and now I'm in business. So now I can say Y encoded dot fit. What do I want to fit? I want to fit this Y output data. So I'll select this and pass this over here, Control V. So now I'll run this, everything looks good. Now I want to now do the transform. So Y encoded dot transform, and then I'll pass in the data. Let me pass in Y output over here, not Y encoded, Y output. So now when I run this, everything looks good. So now instead of having the iris setosa, iris versicolor, and iris virginica, now I'm having 0.00001, I mean, and the ones we saw over here. So this is something that we are quite used to, and this shouldn't surprise anyone here today. So let me rename this into Y output is going to be equal to this. So now when I do a preview of my Y output, I get this showing up. So now I have this as my Y output, and now I have this. Let me do the X inputs for everybody to see. So over here, what I'm trying to say is, okay, we are going to grab this feature, which is a 5.1, multiply by some random weight, plus a 3.5, multiply by some random weight, plus 1.4, multiply by some random weight, plus a 0.2, multiply by some random weight. And that output is now going to be compared with 0. So maybe that output is maybe a 0.5, or maybe a 0.5. So a 0.5 is not exactly 0. So it's going to be 0 minus a 0.5. And we are going to have some negative something or some positive something that's going to be used to update the weight like we saw. Okay, so now everything is looking good. Now we need to split our data into a training part and a testing part. And this is the part we have over here where we are splitting this data set into. Now we have done this splitting. Okay, we have our input and we have our output. Now we need to split it into the training part and the testing part. So in order to do so, we're also going to fall on sklearn. Okay, this scikit-learn is going to help us a lot. So I'm going to say from sklearn.model_selection. There's a method over there called model selection. We are going to import train test split this way. So I'll run this and everything looks good. So now let me just create some new cells below here to see exactly what this is. And we are going to, in fact, I'm going to explain why we need this train test split. So over here, I'm going to say X train, comma X test, comma Y train, comma Y test is going to be equal to this train test split. I'll bring this one over here. And this is going to have the data. So the data that we need is the X inputs, which is this one, the X inputs, okay, and also the Y output, which is this categorical data, because we want to split this, and also the Y underscore output, as we have over here. And then we specify a test size or a train size, okay? Now, the general rule of thumb is, okay, we specify, we want the majority to be with the training. It's almost like, okay, the way this one works is almost like we are going to write an exam, okay? So you have, let's say, some past questions and the answers. So you learn, okay, this plus this plus this is going to give you this. Then you are going to now do a testing. So you may want to learn more. Let's say if you have about 100 past questions, you want to learn about, let's say 80 of them, which is 80%. And then you now want to test yourself without looking at the answers. If you solve the question, a similar question, are you going to get the desired results? That's basically what you want to do. So you want to specify a test size. So I'm going to say test underscore size over here. And I'm going to say a 0.3, which means the training size is going to be a 0.7, which is 70% for this one to be 30%. So now I run this and everything looks good. So now let's do a preview. And there's a very important thing I want you to take note. Now, when I do X-train, we have this showing up over here. And then we see that, well, initially, the original data sets, if I'm to go back, is that we have 150 instances or rows. Now, 70%, because this is going to be the X-train, the training part, is going to be 70%. Now, it turns out that 70%, let me say 0.7 times 150. If I run this, I get 105. Is that okay? So after running this through and specifying that, okay, the test size is supposed to be a 0.3, which is 30%, for the training size to be a 70%. Now it turns out that we have 105, which is actually 70% of the initial chunk. So everything is looking good over here. But then one other important thing I want you to pay attention to is the fact that, well, when we are applying this train test plate method, it is randomizing the order in which the data appears. So over here, these are still the indices, okay? We see that we have, the first one we see over here is 129. The next one is 13, then we go to 14, we go to 20, 74. So everything is randomized. Now, it is better because we don't want a situation where our model is learning on a pattern based on the way the data is presented. It's just like those of you who have written some exams like, let's say, SAT and GRE and some other exams, when we are learning the vocabs, okay, the vocabulary, and let's say we are using cards, okay, you would want to shuffle your cards so that you don't learn based on a pattern, but you learn randomly. And that's exactly what you want to do over here, because if it is by learning by patterns, then the computer is actually going to learn, and that's going to lead to what Dr. Mills referred to as overfitting, because we are overfitting our model, but we want to randomize things. It's like that the first learning is going to pick up on row this, then it's going to jump to row this, it's going to jump again to row this, so it is not following that particular pattern that was initially presented in our data set. And that's why we need to use the train test plate. Okay, so now that's going to be the training part. Now let's also check the testing, the X test, okay? Now we see that the X test is a little bit small, and when we check this over here, we don't get the actual size. But then when I do a dot, let's say a shape over here, we get to see that this is a 45 by 4. The 4 is the number of columns, and the 45 is the number of instances. When we add this 45 to the 105, we get a total of 150. So it actually tells us that, okay, the testing part is actually picking up this 30%. Now let's also check the Y train. Remember, the Y train is going to be something from this, okay? This is a Y output, so it is going to be something from this. And over here, when I run this, I get some NumPy array, and you can see that initially everything is structured in 00001111222. Over here, because of that randomization, we get 20010. And over here too, we can check the shape. So when I do a dot shape over here and run this, you can see that I have 105, there's a 1D array, so I don't have anything for columns over here. And we can actually check by just counting the number of opening brackets, that trick I showed you. All right, so everything seems to be working in terms of how we have structured our data set. Now let's go into building the model itself. So now, with this particular instance, we have our X1, X2, X3, and X4, 4 inputs, sepal length, sepal width, petal length, petal width, okay. And then we expect 3 outputs at the output end of our layer. And that's simply because we are expecting 3 classes. And then we are just going to have 1 layer in here, which is going to be because we are building a shallow neural network. So over here, let's build the shallow neural network model. So I'm going to say from Keras, which is the library we are going to use to build it, I'm going to say from keras.models, I'm going to import sequential, okay. Then I'm going to say from keras.layers, I'm going to import dense layer. So these are the 2 things that we are introducing today. Everything we've seen over here, okay, in addition to this, is some things we have seen before. But then over here, we want that sequential model so that things will be put in that sequential line. Is that okay? And then we have the layer where we are going to have a dense layer. That means we can stack 1 layer on top of each other, in terms of the neurons. And that's what we are going to do. So now I'll run this and everything is working good. So now let's build the model itself. And over here, I'm going to say model is going to be equal to sequential this way. So this is more or less giving me the skeleton of the model. And that's going to be something like this, the sequential model. So I'll run this. Now, what do I want to do? I now want to be adding the layers. So now I can do model.add. Now this add, I need to specify the layer I want to put in over there. So now I'm putting a dense layer. This is almost like this. Is that okay? I'm putting a dense layer. Now inside of this dense layer, I need to specify the number of neurons I'm putting in there. So at the first layer, which is what I have over here, which I didn't put any, I'm just going to put 4 neurons over here. So I have 4 neurons in here. Now I need to add in some few things. And the other thing I need to put in over here is the shape of the inputs. The input shape is going to be 4 comma. Now let me show you why I'm doing this 4 comma. Because what I have as X string, okay, is the entirety of everything. But then the layer is going to accept the numbers, this number, for instance, for this input, okay, this one for X2, that one for X3, and also that one for X4. And for which reason, I cannot just put everything inside of it this way. I need to specify a shape. So now let's grab this particular one. So when I do xstring.lock, remember the lock, and I pass in 129 and run this, I get this particular one. Now let me do a dot shape on this to actually see the shape of this. If I select it individually, this shape is going to be a 4 comma nothing. It's almost like a 1D array. So that's why I'm saying that, okay, based on what I have over here, the input shape, and later on when we deal with other complex data structures like images and other things, we are going to see that those ones are also going to come with their unique input shape. So over here, the input shape is what I'm specifying over here as 4 comma. And that's simply because I want to make sure that it conforms to that original data inside of the data that I have over here. So that's going to be my input shape. So now let me just get rid of this. And let's...
Ken, can you give me 1 minute?
Okay, no problem, sir.
Yeah. So I just want you to explain that in the context of matrix operation. When you have one-dimensional and those sort of things, that will give them.
Okay, all right, sir. Okay, so it is very important to look at this input shape, okay, like rightly Dr. Milson, in that matrix operation, because you see, when we are multiplying matrices, dimensionality matters a lot, okay? And this is what I mean. If we have, for instance, let's say a 3 by, let's say a 2 by 4 matrix, okay? If you are multiplying this by, we cannot just multiply this by anything, okay? We cannot, for instance, multiply this by, let's say, a 2 by 2 matrix. This is not going to work because the number we have over here in terms of the dimensionality to the column of the first matrix should conform to the dimensionality of the row of the of the second matrix. So the general rule of thumb that I tell students all the time is, okay, this is possible. I wish we were in a classroom to actually work out some examples, but I think this is something you should know by now, that this should conform to this so that the resulting output is going to be a 2 by 2 matrix based on that general rule, okay? So over here, if we have, let's say, something like, okay, so let me do x is equal to np.array, and let's just have a 2 by 2 matrix. So let's say I have 1, 2, this is the columns, okay, so 1, 2, 3, 4, comma, and let me have 6, 7, 8, 9. Let me just comment these ones out. Okay. So when I do this, we have this, okay? We have 2 rows, 4 columns. And if I'm to do a shape over here, that's exactly what you see over here. Okay. Now let's work out another one where we have, let's say, one that the dimensionality doesn't fit. So one that the dimensionality doesn't fit, let's say I have this, and let's say I have 2 by 3. So 2 by 3. Okay, so now let's do this. Y is equal to this. And okay, I need to bring, okay. So this is going to be a 2 by 3. Good. Now, if I'm to do Y dot shape, this is a 2 by 3. All right. So now I'm saying that this one, we have, the first one is a 2 by 4, and we are trying to multiply this by a 2 by 3. And I'm saying that this is not going to work because if this, as we have over here, 4, is not matching up with the dimensionality we have over here, then we are going to have some problems. So over here, if I'm to do X multiply by Y, we get a problem over here. It says that the operand could not broadcast this into this. And this is based on what we know, okay? But then the issue I'm saying that if it is, let's say, a 4 by 2, so let's maintain the first one as this, and then let's maintain this as a 4 by 2. So let's say I have 2 columns over here, and now the number of, how do you call it? The number of rows I have, I want 4. So let's say I want 10, 4, sorry, and then a 4, 4 over here. So this is our X, okay, and this is our Y, and sorry, yes, this is our X. So our X is a 2 by 4, and our Y is a 4 by 2. So now when I do this, it says, let me do this. NP dots. Okay. So the dots operation over here. So when we do this, we end up getting a 2 by 2 because the first one over here by the second one over here. I think this is something, this trick is something most of us are quite familiar with. Let me see by hand those who are familiar with this trick. Because before we multiply matrices, we need to check the dimensionality to check if they are compatible. Yes, very good. Sheriff says he's quite familiar with them. So yes, so that is showing up over here. And then also we are going to realize that with when we deal with for instance with images, their input shape is a little bit different. And over there too, we are going to specify that particular input shape over here. But just as we know, like I just showed you, the input shape of whatever thing we are slicing over here is going to be a 1 by something or a 1 by nothing as we have over here. And then you realize that we made mention of the activation function. So over here too, we are going to specify activation. And the activation is going to be a ReLU over here. So this is going to be our first layer, which is going to accept the inputs. Now let's go to a second layer, and I'm just going to copy this, Control-C, Control-V over here. And with the second layer, let's say we have 5 over here. So I just want to replicate what I have over here. So I have 1, 2, 3, 4, 5 neurons. And then over here, I don't specify the input shape because that input will be already accepted by what I have over here, which is going to be connected out of the fact that this is a sequential model. That's a skeleton of it. And then the activation tool, we are also specifying a ReLU. Then we go to the last layer as we have over here, which is going to be this 3 neurons, and each neuron is going to represent a class. So I'm going to do model.add, and over here too, I'm going to specify a dense layer. I'm going to pass in 3, how do you call it, neurons, and then the activation, I'm going to say softmax. Now, trust me, today the main objective is just to build the model. In other examples, we are going to go through deep into why we select some of these activation functions and all that. But I remember Dr. Mills gave us a preview of the various activation functions and what they mean. And over here, the names are looking a little bit different because of how they are called over here. But this ReLU is a rectilinear function, okay? Then we have the softmax. There are other activation functions that we are going to learn. So over here, what we see over here is nothing in terms of architecture as what we have over here. Because over here at the input layer, we have 4 neurons accepting an input shape of 4 by whatever thing we saw over there. And then in the second layer, this is just a shallow neural network. So we don't have a lot of deep layers in here. We have 5 neurons over here, and the activation function is ReLU. And then in the case of softmax, the last layer, we have 3 neurons over here with this showing up over here. So now when I run this, everything looks good. So now let's go back into what we see over here. Remember, at the end of the day, it is the weight that's going to do the magic for us. And at the end of the day, it is the weight that we are going to store. So now let's check the weight. Now I can do model dot let me do model.summary first. So this is going to give us a summary of our model. And clearly we see that based on the structure we put out over here, the output shape of the first layer was a dense layer, is what we see over here. This was fed into another dense layer, and this is the last layer as we have over here. And we have some parameters or params over here. And these parameters are nothing but the weights, okay? So for instance, on the first layer, we have parameters of 20. We have parameters of 20. And we can actually do the calculation ourselves, because look at this. We have 1, 2, 3, 4. And this 1, 2, 3, 4 is being fed into 5. So every one of it has 1, 2, 3, 4, 5, weights. So multiply by 4, we are getting our 20 over here. In the same instance, we have this 25 over here. And something interesting is happening over here. So the 25, this is what we have. This is coming here. So we have 1, 2, 3, 4, 5. Now 1, 2, 3, 4, 5. And then we're having 3 over here. So each one, 1, 2, 3. So this is going to be like 3 by 5, which is going to be 15. Okay, 3 by 5 is going to be 15, but we are getting a 25 over here. We are getting a 25 over here because, let me see. So yes, we are getting a 25 over here because now inherently some biases will be added up over here to shoot the weight up to 25 in terms of the parameters. And then we also get the same for 18 over here. So now, once again, like I said, this is just a summary of the model. So it tells us that, well, the model is a sequential model, and these were the layers that we stacked next to each other. And then the total parameters over here, the total trainable parameters are what we see over here, and the total non-trainable ones are what we see over here. So now let's get the weight. So now I can say model.get_weight. So when I do model.getWeight, wow, these are interesting things we see over here. So these were the randomly generated weights that were specified or were given based on the structure that we put out over here. And once again, we are going to there's a weight. We haven't done the training yet. Now, after the training, the weight is going to change. So let's save this get weight as initial_weight. Is going to be equal to this. So this is the initial weight. And then after our training, we are going to get the final weight, and we are going to do the comparison of that initial weight and the final weight. So that's what we see over here as our weight. So clearly over here, you see that with the first input, okay, we have 4 neurons. So each one, okay, this is 1, 2, 3, 4. And remember this, this like going to be the weight that's going to be assigned to the sepal length, sepal weight, petal length, and petal width for the first inputs, okay? And then the other ones are also going to show up over here. And then we have some biases over here, 0, 0, 0, 0 for each of those neurons over here. Now, with the second one, we have the randomly generated weight with some biases over here. And with the third one, we have the randomly generated weight with some biases over here. So now we want to compile the model. So now I can do model.compile. And the way we compile our model is, okay, we pass in all the parameters that we need. So we are going to use an optimizer. And this optimizer is very important because if we don't use an optimizer, our model is going to run till God knows how long, okay? So we want to put some measures in place so that at least it converges at some point. So the Abnam optimizer is what we need. And later on, we are going to see that, okay, it is actually at the optimizer level that we can specify the learning rate, whether we want to learn at very large steps or very slow steps. So we pass in the optimizer over here. And now we pass in a loss function. Over here, we are going to use the sparse categorical underscore cross entropy. So sparse categorical cross entropy. And we are going to measure the metrics of accuracy. So I'm going to say accuracy over here. Okay, now everything looks good for me. So over here, we are compiling the model and we are specifying that I want to use the Adam optimizer, and we are going to use the sparse categorical cross entropy, and we are going to measure, or we are going to monitor the accuracy. So over here, I can do model.fit. This is where I bring in the actual data. So model.fit, okay, what do I want to fit into this model? I want to fit the X train and the Y train so that the system learns from it, okay? This is what we want to fit. We want to fix X train and the Y train. And later on, we are going to use this to make some prediction. And out of the prediction, we are going to compare it with this original one to see if the prediction was actually good. So over here, let me come down here. Model.fit, I'm going to say X train, Y train, and then I'm going to specify an epoch. The epoch is going to be the number of iterations. So over here, let me just say 50, and now let me do Control Shift Enter. So the training is being done, and this is a very small data with not too complex structure. So we get, and look over here. So upon the first epoch or upon the first iteration, our accuracy started at about 45%. It went on to 48 upon the second iteration, 49. So it was actually gradually increasing. It went up and came down, and then it ended up at 50. That's not too good. It ended up at 58%. Don't worry. Other models, we are going to learn how we can better enhance the learning process. One of the things we can do is, okay, sometimes we can just, for instance, increase the number of iterations, okay? And now let's do 100 epoch and see. So 100 epoch, okay, this one is looking good. We are about 70, it is dropping, and 80 is going up, 70, so it goes up, goes down. Okay, it ended up at 87. Okay, so maybe we can keep this one, okay? So 87% accuracy is not too bad, at least for our first model that is not too complex. All right, so now let's get the final weight to actually do some analysis. So I can do model.getWeight, and then this is a final weight. So now let's compare this with the initial weight. So let me just do this initial weight, initial underscore weight. Okay, I think the spelling. Okay, so let's just look at the first instance we have over here. We had a randomly generated initial weight of 0.365, and then after updating and going back and forth, it ended up at a 0.373. All right. The second one we have over here was initially was a 0.206. It ended up at a 0.299, so on and so forth. Okay, so we saw that, or at least we've seen that the weights were being updated based on the mathematical computation we saw over here. This was just a brief snapshot of just one particular one. Over here, we have about, based on the model summary that we see over here, we have about 63 of these, okay, randomly generating, and the epoch, the number of iteration, about 100 times. So it went very far, but then because of the system that we are using now, we could see that clearly the model was able to build very quickly. Now we've come to a point where we can do some plotting over here, but then our time is up. So let me just quickly conclude on this evaluating of our model so that we can actually see our model in action. So now our model, this model is just a complex, okay, okay, this model is going to be some complex structure of these weights, okay? A complex structure of these weights. And now when we try and do a prediction, it is going to multiply our values by these weights and it's going to give us some value. So now let's look at this. Now, let's do model.predict. And over here, I'm going to be very quick, but then please pay attention. So model.predict, okay, so now we've built our model with our training, X train, and then our Y train. We want to test, so we can do a prediction over here. So I'm going to pass in the X test over here. So I'm going to say X test. I'm passing X test over here. And now when I run this, I get some values shown up over here. Now these values are quite interesting. But then what this prediction does in terms of what we've come to understand is that this one will give us a probability distribution of, okay, so the first one over here is saying that, okay, in terms of the first class, based on the testing data that you have put in over there, I'm giving you, and this is e to the power -3. So this is 0, this is a very small number, okay? And this is equally a 0.49, and this is a 0.5. So at the end of the day, this is the biggest one, okay? Now, it turns out that what we see over here, let me call this y_predict is going to be equal to this. So now let's do a preview of this proper and do a proper analysis of this to see. So this is what we have. Now let's just slice the first one, okay? The first one we see over here. So let me just slice and pass in an index of 0. So when I do an index of 0, this is exactly what I get, okay? If I'm to do this, this is what I have over here, okay, with the index of 0. Okay, so now having this, or now that we have this, we can see that, okay, now it has stripped down everything for us. It is telling us that for the first instance, when we pass the X test into our system, it is giving us a probability distribution that, okay, if it is the first class, it is about a 0.0005%, which is very low. In this case, it is about a 49%. And in this case of the second class, or sorry, the third class, it is about a 50%. So it is very close over here. And later on, I'm going to tell you why. So now let's look at this actually. Now, what we've done over here is to be passing the Y test. Okay, the Y test is what we see over here. Sorry, the X test. We have passed this data into the model to make some prediction. Now let's compare it with the actual Y test. So now let's see. If I say Y test is the actual value. It is telling me that, okay, for the first one, the label was supposed to be a 1, but then we are predicting a 2 over here. I'm starting counting from 0. So this is a 0, this is a 1, and this is a 2. It is supposed to be a 1, but then, so it was supposed to be this, but then it is telling us that it is this. Remember, our accuracy is about 84%. Sorry, 87%. So definitely it didn't get all of them right. All right. But then let's look at the second one. The second one, which is going to be the prediction from label 1, we are seeing that, okay, the second one, it is about 95% sure that this was label 0. And indeed, it was over here too showing as 0. And of course, if it is 95%, then the other ones are going to be significantly small. Let's check for the third one, which is also going to be a 0. So the second one was 1 with 2. And then we get to see that this one too is about 96% sure that it was a 0. We see a 0 over here. And the other ones are woefully insignificant. Now let's do the fourth one over here. So this is 0, 1, 2, 3. So let's do the 3 over here. So the 3 over here, it is telling us that it is label 2. Okay, it gets it right over here, about a 55% that this is label 2. But then once again, it is very close as we have over here. So we can go on and on and on. But then let me just quickly run through this. So let's do our Y predict. And we get this. Now, what I want to do is, if I'm to grab, for instance, the first one as I did, okay, this one. And I'm to do dot sum, everything is going to sum, all the numbers over here is going to sum up to 100. So that's what you see over here, 1.0. So like I rightly said, this was giving us a probability distribution based on the percentage. That's okay, based on the data you have in there. This is about how much it is closer to this particular class than it is closer to this particular class. That's basically what we have over here. So when we do it this way,
Ken, can you pause for me 1 minute?
okay, all
So
right,
please, when you go back, you remember that when we started talking about the activation functions, one of the functions that we talked about was the softmax. And the softmax, if you refer back to the earlier slides that we gave to you, softmax works on the principle of what we call probability distribution. All the node points that we have, it tries to find out what is the probability that a particular category will fall into that, and that category is based on the one that has the highest probability number. So when you look at all the outputs of each of them, when you sum them up, it's supposed to give you 100%. So if you get back, you can refer to the first or second slide that we gave to you that shows the activation functions. And then a typical example on the softmax. If we were to deal with only two binary states, then we are not going to use a softmax. Then we could have used maybe a unit step,
yes,
or a hard function. So based on what output we are looking for, then we can use the appropriate activation function for it. Okay.
all right, thank you very much, sir. Now, there's also one thing I would want to point out that, so for instance, we are picking the second one, which is this almost 90% or sorry, 95% thing over here. Okay, now there's a function in NumPy, okay? If I'm to do np.argmax and I pass this over here, what I'm trying to say is, okay, I just want you to give me the label of the maximum, okay, the argmax of this particular thing you have selected over here. So the label is actually going to be based on the position it appears over here. So over here, the label is going to be a 0, okay? In the instance of the first one, where, let me just get rid of this first. In the instance of the first one, 0, where we're predicting a 2, okay, because this is 0, 1, 2. If I'm to do np.argmax, we are getting a 2 over here. So this we are going to use to do something very interesting. So now, if I'm to do this ypredict, this original ypredict is going to give me everything that has been predicted. Okay. And now what I want to do is, okay, I want to run a for loop. So I'm going to say for the prediction or the predict in ypredict. I want to, for instance, do a printing of the predict, all the predict values. So when I run this, I'm getting this. Okay. Now I'm looping through and getting this. And now what I want to do is, I now want to do, for instance, np.argmax, and then I want to pass this out over. When I run this, it says, okay, I'm adding too many. Yeah, np.argmax. I have this over here. So now let me print this one out. So I have this, everything being changing to the argmax over here. Now what I want to do is, I want to have, let's say, y prediction is going to be equal to an empty list. So now what I want is, I just want this empty list. Okay, this empty list dot append, because it is some kind of a list. I can do an appending. So instead of running this loop and printing out this way, I just want to do an append. So now when I run this, everything looks good. So now when I do a preview of this, I have this in a list, but then I want to change this into a NumPy array. So I can say np.array, and I'll pass this once again. So now when I do a preview of my Y prediction, I have this. Now it is this prediction that I want to check with my y-test. Remember, my y-test is what I have over here. This is a y column, okay, and this is a test. And I've passed the x-test into my model to make some predictions. So I now have some values. Maybe this one is 1, 0, 0. Maybe the one I had was 0, 0, 0. So I want to now do the comparison and see. So over here, you realize that, of course, the first one was supposed to be a 1, but then we predicted a 2. But then we go on to the second one. We see a 0, 0. We see a 0, 0 over here. We see a 2, 1. We see a 2, 1 over here. We see a 2, 2, which was a prediction, but then the actual was a 2, 1. Then we see a 1, 2. We see a 1, 2 over here. We see a 2, 0. Of course, we see a 2, 0 over here. We see a 2, 1, 0, 0, 1. 2, 1, 0, 0. So clearly, it had a lot of them right. And that's why we got an accuracy of 87%. But then definitely not everything was right, because if it is 87%, then some of them were wrong. And that's why we see this particular one as a prediction of 2, but then the actual was actually a 1. Now we can go on and on with this. I don't know, Dr. Mills, should I continue with some of the things I want us to do, especially with the analysis, or we'll conclude on that on Thursday?
I think we should conclude on that on Thursday. It's loaded now. So
okay. All right.
I guess we can pause here, and then if they have any questions, they can ask.
Okay.
Then if not, then we close. And then Thursday, we'll wrap up with the rest of the discussion.
Okay.
So the floor is open now for suggestions, comments, and suggestions, comment, and questions. Yes, do we have anybody, any question, comment, or suggestion? You raise your hand and then we'll call you. Okay. So the last call.
Okay,
okay, Sheriff.
Mm-hmm.
Yes, thank you very much for such a beautiful presentation. I've really learned a lot, and then it was very pragmatic. Thank you very much. Please, my question is, you see in your presentation, you try to, when you're using the linear regression approach, you came up with a formula. I mean, the relationship between y and x.
Yes.
So when you want to build a model or something of that sort for a machine learning something, I think you are going to input that same equation into the language, the Python programming language, and then use that. So I don't understand when you say machine learning doesn't use programming. I don't know if my question is very clear.
No, you are not going to write the equations. So for now, that aspect is talking about was a regression.
Yes.
Regression model. So we have one of the machine learning models or algorithms that we call linear regression. And there are different categories of it. One has polynomial, one has multiple, like most of the things you know in statistics. But this one is purely data-driven. So when you do your model will give you some equation or some solution that will boil that down to the equation that he has spoken about.
Okay.
You are not going to write equations.
Yes, let me also add up to this. Okay. So, Sheriff, now you agree with me that this equation of a line, as we see over here, okay, is dependent on the plots, the data points that we have over here. So, for instance, if there was, let's say, another data point where we had 25 and the weight was 70, we're actually going to have age 25 with a weight of 70 showing up somewhere over here. And that can significantly affect the line of best fit. So we are not going to hard code this equation of that straight line into our code. We are just going to present the data and tell our system that we want to use a linear regression model. It is inherently going to have that line of best fit for us. So if we are to go by hard coding the equation, then that wouldn't be a machine learning, because then in that case, any data that comes in there will suffer. But then, and when I say suffer, means it is not going to have a very accurate prediction, but we are going to make the model learn from the data that we have and figure out that line of best fit, which, I mean, if with the example I just cited, let's say we have 25 and 70, it means that, okay, if that line of best fit is going to join up with that line, then it is definitely going to tilt the slope, and eventually going to have an impact on the slope and also the y-intercept down here, which is pragmatically going to affect that learning rule. But then we just present the data, specify that we want to use a linear regression model, and it is automatically going to figure out our coefficients and everything for us.
So this is what I do, because this is all, again, if it was a theory class, then what I do with students for theory classes, we will not use the Python for this. You will write the whole script yourself based on the mathematical function that we use to implement this. You see that when he was using the shallow learning, before this, he showed you what you call x multiplied by something, x times w plus s times w. So depending on the number of input variables you have, if you have 5 input variables, you are going to have S1, S2, up to S5. And then each of them, we're doing the product S1 times the weight 1, on and on and on. Now, exactly this one, you see that all these things, he didn't write it in the code. All this, what he did was he only put the functions there. That is why when we started, we explained these things to you, because codes that the model or the algorithms that have been written, they were written based on this function. But they will not tell you that the line is supposed to be this or that. They will just write the function that's supposed to be implemented for the operation. Please, I don't know whether you are okay with the explanation.
Yes, Doc. Yes, Doc. I get it now. Thank you very, very much.
Any further question or comment?
Okay, Philemon, you can proceed to ask your question.
Okay, with the model fitting,
yes,
when you run it multiple times, the accuracy gets better, because the first time I ran it, the maximum accuracy I got was 37%.
Okay.
But after running like a couple more times, I got 90%. Why is that?
Okay, so
yeah, so okay, Ken, go ahead.
Okay, so it is obvious that definitely some overfitting is being done over there. Okay, now it may be good, it may be bad in a way, because a lot of the time, if you are presenting data to a model for the first time, especially when it doesn't know anything about the data, the weights are going to be randomly generated. And if you are to critically look at the weight you had, okay, and compare it to the weight that I had, they are completely different from yours. I mean, my system is different, your system is different, and it's going to be that random generated data of weights. And at the end of the day, if, let's say, you had a good start with a random generation, because, for instance, look at this one, for example, this one was the initial weight. It started at 0.6, and then the final weight, where is this? Sorry. So the initial weight, this one, it started at a 0.65, okay? This is the initial weight, 0.65. And the final weight, it ended up at 0.7. In fact, if we are to round this up, we are getting a 0.7. So clearly, you could see that, okay, based on the initial weight and the final weights, it didn't change that much, okay? Because it was able to learn and realize, okay, at this point, if I am to update it further, it is probably going to miss the mark. So let me stay within that close proximity. Now, the point is, if you run your system the first time, some weight has been learned, or some weights some knowledge of the data set has been known. If you run it for the second time, it is only going to more or less better it in some cases, or in most of the cases. In some cases, it may further degenerate and make it even worse. So it depends on how the data set you are presenting and also the random weight that was initially generated in the process. I think that's where I mean, that's what I'll say for now. Maybe Dr. Mills can add a few more.
Yeah. Okay. So based on see what the equation that he shared with you in terms of the weight change and then the error. Now, so if you recall again, when we started the discussion, we took you through some basics, and I asked you to do something in the Huawei lab. We were doing calculations. Now, if we have 100, so what he has about, I think the training data set was 105 samples or 105 records. So each record has S number of inputs and then one output. So for iteration, we will take sample by sample, and then you take the first sample, and then you find out the error. If the value, if the correct class is given, it means that there's no error. Now you go to the second sample, go to the third sample until you get to the 105th sample. When you run through all the sample one time, that will give you one epoch. That's what it is. So one iteration, that's what it is. Now, so if you decide that you only do just, let's say, 5 iterations, it means that to run that's all the set 5 times. And that is okay. But if that is not the situation, it means that the more now the question is, how far should we go? Should we go 1 million iterations? No. We'll get to a point where you see that there is stagnation. In that case, there's not much that can be done about it again. If you are still not getting good results, then there are possible things that could happen. One is your learning rate too high, or your learning rate is too low, so you play around with the learning rate. So normally when we are doing these things, we start with a reasonably low learning rate, and then we keep adjusting the learning rate over time. Now, when you are dealing with some optimizers, they will adjust the learning rate by themselves. And for some, you fix them as and when you go along. So the iterative process is mainly how many iterations you will go. There's no rule of thumb anywhere that will tell you when you have this, go this, no. So that is how the beauty of the training is about. And then when you get to a point where you think that you have got something reasonable enough, that is what it is. So in most development that we do, we always ask you do a lot of comparisons. You run the first step, you go again, you run the second step, you go again, then you compare the first and the second until you get one that will give you the best results. In this particular instance, he has fixed, for example, 5 neurons at the hidden layer. First in the 5 neurons. Can we go 10 neurons? We can do that. So there are a number of adjustments that we do in order to come up with the optimal solution. So this is just the beginning of the process. Yes, Enoch.
Thank you very much, Doc and Mr. Bruni.
Oh, your line is breaking. I think your data, internet.
Offline, except the import.
Sorry?
Hello, please, can you hear me?
Yes, it's better now. Go ahead.
I'm asking, thank you very much for the session. I'm asking if all this can be happening offline, except the installations and the importations. And then also, how does computational power comes in with the learning? These are machines. Can they support it and to what extent can they?
It depends on. First one is, if I got what you said right, the last one was the computational power of the machines. Is that right?
sir.
And then the first one was what?
The first one, I was just asking if all this can be happening offline, except for the installations and the imports we're doing, because I see the internet connection and all that. I'm just wondering if all this can be happening offline.
It's because of what you are asking, but you can do it offline, right? In terms of, let me just quickly comment on the data, the machine's capability. Now, it depends on the type of model that you want to use, or the type of model you are trying to develop. If, for example, you are looking at, let's say, DNA sequencing, that may involve more high computation because of the numbers involved, then your ordinary machine can take days to do the computation for you, the model development for you. So under such circumstance, then we can resort to HPCs, high performance computers, to do that job. Otherwise, then you have to have some para processors also that will help you to do that. But cases that we have done, some students that we have worked, they spend 3-4 days sometimes to do some very complicated model, 3, 4, 5 days to do that. So the summary of it is that it depends on what solution you are developing. Ken, is there any comment you can add on or subtract?
Oh, no, sir. I think you just hit the hill right on the head. So it depends on the model that you are building and also the data you are dealing with. So if you are dealing with, let's say, high resolution data sets, and later on you are going to understand where, especially when we start dealing with images, how computationally expensive it can be, because there are a lot of numbers in there. And if the resolution is very high, that means you have a lot of details in there. The model or the system needs to crunch all those numbers, do the matrix multiplication and all those things. Okay, if you are doing it by hand, you can imagine how laborious it's going to be. So imagine the computer doing it. So like Dr. Mills rightly said, we can use the high performance computing machines to do that. Or if it becomes extremely necessary, then you can probably sublet that computation to, let's say, some cloud computing resources like AWS or Google Cloud or Microsoft Azure, where you can actually, let's say, a very high computing machine for, let's say, about a day. Maybe you pay about, let's say, $10, which is, I mean, depending on the kind of work you are doing, and you can actually run your model very quickly.
I was going to come to that aspect, the public processes available.
Yeah, sure.
I'm doing some work. We are doing some work with industry, and then we needed high power. So, of course, the industry, they can pay. So we are using AWS.
Okay.
And they are paying for those clusters. So we are running, because we are dealing with millions of data set for fraud detection, for financial data. So millions of transactions. And that one, what we try to do is AWS, you have the various clusters. So you are running different, you call it a para processing. Okay. So you are push one part to run this, other part to run this, other part to run this. That's how it is being done. Okay. You have to get, there's some of them, for example, 24 hours, we are still working, doing some model. So it depends on what solution you want to have. But normal students' work that we do in final year, graduate level project, things like that, some of them have been run on their machines that sometimes it takes them a few days. Of course, it's your machine. So you run it and your machine is lying somewhere, then you are also doing something else. But if you want some serious minded something, then you have the money, then you can buy some processing power from some of these developers around. At least I know AWS, and then you also mentioned the Google also as well, and then also the Microsoft. Enoch, are we okay?
Very okay, sir. Thank you.
Okay. So if there are no further questions, we have eaten well deep into our time, and we have taken some of your time as well. So if there are no further questions, please please, in your own spare time, just go through what we have done today, and then Thursday we will continue to wrap up. There are other more things that we will be doing, but step by step at a time. As of now, we haven't taken you through, for example, how to measure the performance. All that we have just said is we said accuracy metric. But honest, if you look at the schedule that we're giving to you, there are also segments that we are going to get into it, details, how to measure all these things, and then what type of metric do you use for what application. So we'll get through all these things. If there are no further questions, then we'll close for the day. We thank all of you for your participation.
Right,
Ken, also, thank you very much for the presentation as well.
Oh, thank
I
you
hope
very
you are
much.
going to share the everything on the platform for us.
Yeah, sure, sir.
Thank you.
Okay, bye.